So this is the 11th session on rigid body kinematics. So in this session also I will take up some more numericals on rigid body kinematics based on SRC procedure for velocity, okay, as has been discussed in the previous videos. So you must to come to this, if you directly go to this video first, then that will not be all right. First you must be fully aware of the theory underlying these numericals, okay. So for that you have to discuss from 7th session. If you see 7th session on rigid body kinematics, 7th video, there you'll get the theory for the class of numericals which are going to be discussed in this video, okay. And in case you know the theory, then it's all right, fine. So I'll take up another problem, okay. Let's write down the question, okay. P1, P2 is a vertical rod of length L and its upper end is in contact with a fixed vertical wall and its lower end P2 is in contact with a horizontal surface. Starting from P0, lower end of the rod is made to move along positive x-axis at a constant rightward speed v, okay, as shown below. All right, fine. Find the angular acceleration beta of the rod as a function of time t by several methods. Okay, this is the question. And other quantities L and V also can appear in the answer. So answer should be in terms of L, V and T. Alright, fine. So now this I'll rub it, okay. Such a coordinate system is also shown in the diagram. Okay. So before solving this question, one thing I would like to say: if you carefully go through these videos containing these numericals and understand them thoroughly, and then you try numericals from some other source, definitely I think you will be able to solve most of them. I don't think there is any doubt about it. Okay, if you understand all these numericals properly and you carefully go through the theory of these videos, then if you go through it and you understand it properly and then you try numericals from any other book or any other source, I think you'll be able to solve most of them. There's no doubt about it. Okay, fine. So now, first what I'll do, I'll draw the diagram of the situation. Coordinate system is also given in the problem. Okay. So this is the coordinate system. Coordinate system is fixed to the ground. Horizontal ground is taken to be the rightward x-axis. Upward vertical is the y-axis. This is the vertical wall. Okay. This is the origin of the coordinate system. This is the initial situation of the rod. Upper end of the rod is P1 and lower end of the rod is P2. P2 is initially at origin. Okay. And P1 is the upper end of the rod. P1 is the upper end of the rod and P2 is the lower end of the rod. Length of rod is L, rigid rod. P2 initially coincides with origin and P1 is initially on y-axis. This is the rod at time 0. Now the lower end P2 of the rod is made to move rightward at a constant speed v. So as this P2 moves rightward at a constant speed v, P1 will go downward. So at some time instant t later, the diagram of the situation will be something like this. And I have written here, okay. So this is the rod at t barabar 0. And t seconds later, P1 comes somewhere here. And P2 comes somewhere here. So this is the rod at time t. P1 comes here at time 0, time t, and P2 comes here. So and this is the rod at time t. Okay. And P2 is moving at a constant speed v, rightward direction. And the rod has turned to an angle theta. Okay. So this is the situation at time t. This is the situation of the rod at time t. And this is the rod at time 0. Okay. So at t time later, P1 has come here and P2 has gone here. Alright. So now we'll solve this question by several different methods. We have to find the angular acceleration beta of the rod, and that is with respect to ground, as a function of time t by several different methods. Okay, fine. So we'll solve this question by various methods. M1. See, the basic approach will be, we find the angular speed omega as a function of time and then differentiate that to get beta as a function of time. Okay. Beta is d omega by dt, where omega is the angular velocity of rod at time t. Omega is the angular velocity of the rod at time t, and beta is equal to d omega by dt by the rule of angular acceleration. So I got this out formula. So angular acceleration beta at time t is angular velocity d by dt of omega. Omega denotes the angular velocity of rod at time t. Fine. So if we find omega, then we get beta also. Alright. So now solve this by several different methods. Fine. So method 1, M1. See, initially P2 was at origin. T seconds later P2 comes here. P2 is moving rightward at a constant speed v. So in t seconds, P2 will move a distance of how much? Vt, speed into time. Now this length is L, L is the rod length. From this we see, in right angle triangle, this is the hypotenuse, this is the base. Vt is equal to L sin theta from trigonometry. Vt is equal to L sin theta. Now this equation is valid for all times. So now what I do, I differentiate this equation on both sides with respect to time. So this I write as d by dt of Vt is equal to d by dt of L sin theta. D by dt, V is a constant. So d by dt of Vt is simply V. L becomes outside, L is constant. And this becomes d by dt of sin theta. Okay, fine. So this I write as L times d by d theta of sin theta into d theta by dt. Alright. So V is equal to d by d theta of sin theta is simply cos theta. And d theta by dt is nothing but omega. So omega becomes V by L into cos theta. This becomes omega. Alright, fine. Now I'll drop this here, okay? Now I differentiate this with respect to time again. So omega becomes V by L. 1 by cos theta is simply sec theta. So I write this as sec theta. So beta is equal to d omega by dt. So this becomes d by dt of V by L into sec theta. Now V by L is constant, that comes outside the differentiation. And this becomes V by L into d by dt of sec theta. This becomes V by L. Now we apply chain rule. So this will be written as d by d theta of sec theta into d theta by dt. So this becomes V by L. Derivative of sec theta becomes sec theta tan theta. Alright, fine. So that becomes sec theta tan theta. And d theta by dt becomes omega. Alright. Now I rub this one, alright, fine. So beta is equal to V by L into sec theta into tan theta into omega. Omega is V by L cos theta. So this becomes V by L into cos theta. Okay, fine. So this becomes V square by L square into sec theta into cos theta becomes 1 by trigonometry. Only tan theta remains. Alright. But answer beta should be in terms of V, L and T. So theta has to be removed. Now from this equation, sin theta is Vt by L. So this can be written as V square by L square. Sin theta, tan theta will be written as sin theta by cos theta. This is how it is written. So this becomes V square by, sorry, this is L square into sin theta becomes Vt by L. Cos theta becomes root under 1 minus sin square theta. Vt by L whole square. Okay. So this is the required answer. This is the required angular acceleration beta of the rod at time t. So this becomes now, this becomes L goes up. You can leave like this also, but if you want, you can simplify also. So this becomes L goes away. So this becomes V cube t by L square into root under L square minus V square t square. I think this is the correct answer. 1L cancels out with this one. Okay. So this becomes V cube t upon L square, and 1L goes away. L square minus V square t square. This is therefore the required answer. Is the angular acceleration of rod as a function of time t. Alright. So this was the solution by method 1. Fine. I'll rub this one, okay. I don't think there is any calculation mistake, no? Alright. Vt by L sin theta becomes Vt by L. Okay, fine. And L goes away. So V cube t by L square. V cube t by L square. Root under L square minus V square t square. Okay, is all right. Now I'll solve this method question by other methods also. Method 2. Method 2, what I'll do, first I'll find omega, okay, in terms of t. And then what I will do, I'll differentiate that, okay. So from that also the answer can be obtained. So method 2, it's like this. This is the rod, okay, at time t. This This is P2 here and this is P1. This is the rod at time t. Okay, fine. This is the rod at time t. So at time t, P2 is moving rightward at a constant speed v, and suppose this angle is theta as was shown just now, and P1 is moving downward at a constant speed v1. Okay, v1 has to be found by some means. Now this rod, you can see this angular speed of omega is of rod is omega. This is moving rightward, this is going downward, so omega is in anti-clockwise sense. Okay. Now omega from that theory is relative normal speed by separation. All right. For if you doubt this concept, you don't know this concept properly, you can go to the first and second video of rigid body kinematics. There you'll get all those things. Okay. So omega becomes relative normal speed by separation. Now this is right triangle, this is theta, so this is 90 minus theta by trigonometry. This extend this also becomes 90 degree minus theta. Omega becomes relative normal speed by separation. Now what is the normal speed of P1? Component of V1 normal to this line, that is the normal speed of P1. So this becomes V1 sin theta in this direction. And normal speed of P2 is what? V sin 90 minus theta. This is V cos 90 minus theta. Normal component of velocity of P2 is component of V normal to this rod, that is in this direction. V sin 90 minus theta. Now these two normal velocities are in opposite direction. So relative normal speed will be the sum of these two speeds. So omega will be written as V1 plus V sin 90 degree minus theta upon separation L. Alright. And V1, sorry, sin theta was left out. This is sin theta. Alright. So omega becomes V1 sin theta. I'll write it again. Sin 90 minus theta becomes cos theta. V cos theta upon L. Now we must know V1. To find omega, we must know V1. The question is how to find V1. V1 can be found in this way. P1, P2 are the material points of this rigid rod. So distance between P1 and P2 is constant. So component of velocities of P1 and P2 along rod P1 P2 must always be equal. Rigidity constant. For this you go refer to the first video on relative velocity. There you will get all those things. So what we'll write? V1 cos theta is same as V cos 90 minus theta. So this becomes V1 cos theta is equal to V sin theta. So V1 becomes V sin theta tan theta. This becomes V1. Alright. So V1 becomes V tan theta. Fine. Now I rub this one. Now I put V1 here. I draw a line here. So omega becomes V1 sin theta. V1 is V tan theta. V tan theta is sin theta by cos theta into sin theta plus V cos theta upon L. So this becomes plus cos square theta by L. Cos theta comes down here. Now sin square theta plus cos square theta becomes 1. So this becomes V by L into cos theta. This is omega. Now this omega is same as we obtained in method 1. So subsequent steps will be same as was that in method 1. So if you simplify, if we derivate this, and again beta, we get the same answer here also as we obtained in method 1 also. Because after this the method is same as in method 1. So our remaining steps are same as in method 1. So I just write down the answer. Okay. So beta becomes V cube T upon L square root under L square minus V square T square. So this is the required value of beta, method 2. Fine. I'll drop this one. I'll grab the first column. Now we discuss this question by method 3. Okay. By method 3 also we can discuss. Method 3 we apply SRC. Okay. By applying SRC. SRC procedure for velocity. Alright. By applying SRC procedure for velocity, whose theory has been discussed fully in the 7th and 8th videos on rigid body kinematics. SRC procedure for velocity. Again, to solve this method 3, what I do, that I draw the diagram of a rod at time t. I draw the diagram of the rod at time t. So at time t it is something like this, as was shown in method 1 also and method 2 also. P2 is moving rightward at a constant speed v. This angle is theta. Is rotating at angular speed omega time t. Okay, length of rod is L. Now, in applying SRC procedure, we have two options. We apply SRC between P1 and P2. We either select P2 and take P1 as other point, or we take P1 as selected point and P2 as other point. We can do any one of them. Okay. So what I do, I apply SRC between P2 and P1 and take P2 as the SP, as a selected point. We apply SRC between P2 and P1 and take P2 as the selected point. Okay, fine. So SRC for velocity, I simply write SRC. So SRC between P1 and P2. Okay, and P2 is the selected point. Fine. Now I have this one. So now what we do, SP arrow P1, we take P1 as a selected point. OP arrow P2, we take P2 as the other point. Fine. We draw the diagram of SP and OP line joining SP OP. This line is this one, so I use this itself. Don't draw it again. Alright, fine. Now what I do, I give the velocity of SP to OP. As velocity of SP is v rightward, so I give this v to P1, v here. Okay. Now I write down the sentence. Sense of omega is anti-clockwise. So other point P1 moves in anti-clockwise circle with center at P2 and radius L. So from this point of view, we get a speed of omega L to P1 at right angles to the rod P1 P2, like this omega L. Alright, fine. Now velocity of P1 is resultant of these two, which is in downward direction V1. So component of these two is in V1 in downward direction. P1 has no horizontal motion. So component of these two in horizontal direction should cancel each other. Now this is theta, so this becomes 90 minus theta. If you extend this also becomes theta by geometry. V is equal to omega L cos theta. And components of these and these two cancel out in the horizontal direction. So rightward component V should balance omega L cos theta. So V is just equal to omega L into cos theta. So cos omega becomes V by L into cos theta. Now this omega is same as we obtained in method 1 and method 2. So remaining steps are same as we did in method 1. So directly from this, if we differentiate it, we get the same value of beta like this. V cube T by L square under root L square minus V square T square is the required value of beta. So method 3 also I obtained the answer. Alright. Now we can apply SRC between P1 and P2 and take P1 as a selected point. That also we can do. This also I am doing it. Okay. Now what we do by SRC between P1 and P2 and take P1 as a selected point. So SRC for velocity between P1 and P2 and take P1 as the selected point and P2 as the other point. Okay. See, sometimes I write SP leftward, P1 rightward, or P1 leftward, SP rightward. That doesn't matter as long as the concept is clear. Okay. So again, I draw the line joining P1 P2 whose orientation is same as in the problem. So this line I draw it here also just for the sake of clarity. Okay. So this is P1, this is P2. Fine. Now I give the velocity of P1 to a selected point to other point P2. Velocity of P1 is assumed to be V1 in downward direction. So I give V1 to P2. Now I write down the sentence. Since omega is anti-clockwise, so other point P2 moves in an anti-clockwise circle whose center is at P1 and radius L. From this point of view, I give a speed omega L to P2 at right angle to this. The resultant of these two should be V in rightward direction. Now P2 has no vertical motion. P2 moves horizontally. So vertical components of omega L and V1 cancel each other. Now this angle is theta. So by geometry this angle is also theta. So now what I will do, velocity of P2 is known to be V rightward. This is known. Resultant of these two is in V in downward direction. So sum of components of these two in rightward direction should be V. But component of V1 in this direction is 0. Only omega L has a component of rightward component of omega L cos theta. That should be equal to V. So omega L cos theta is equal to V. So that same omega we obtained again as it was here. So the same beta we get again by this method. Remaining steps are same as in remaining method 1. So this is again answer by method SRC concept. Fine. Alright. So this Arab. Okay. Now there is method 4 also, using the concept of instantaneous center of rotation, but that theory has not been discussed here. So that will be discussed in the coming videos. So I just mention it here. Okay. I'll mention that here, but then so I'll not go beyond this. Okay. So method 4, I just mention it. Method 4, by using the concept of instantaneous center of rotation, IC. By using the IC concept. So this will not discuss here because that theory has not been discussed till now. So that I will discuss to be discussed in the coming videos. Okay. So when I go to that chapter of instantaneous center, I'll solve this problem by that method also there. Okay. To be discussed in coming videos. Alright. So I have solved this method by several ways. Question by several different methods. If you go through all of them properly, then your concept, if you understand them fully, and then you try numericals from some other book or some other source, then I think you will be able to solve them. Whether it's for NEET or for JEE Mains or JEE Advanced, I don't think there is any doubt about it. Fine. So I close it here. In next session also I'll take some more problems on rigid body kinematics. Fine. Alright.